Hello, my name is Carissa, and today I'm going to run through an example of how we might estimate parameters in the Frequentist and Bayesian framework, and then we will do a t-test example. So before getting started, I want you to ask yourself, do you think there is a difference in the amount of time that men versus women spend on the web? So think about time spent visiting websites, social media, streaming services, chat rooms, online conferencing, etc. So any non-work types of activities. Okay, so this question was actually asked in the General Social Survey in 2022. The General Social Survey collects a variety of opinions of American adults on social issues, and it's started data collection in the 1970s, and it collects data every couple of years. So this is what we're going to be investigating today. Okay, so I have Jamovi open here, and I've already loaded my data set, which is the General Social Survey from 2022. Make sure that you adjust the variables as needed and making sure that missing values are appropriately coded and accounted for. So the first thing I'm going to do is drag and drop our two variables of interest into the correct boxes. I went ahead and I relabeled the sex variable to clearly label men versus women to make it easier to interpret the results. And the next thing that I'm going to do is go ahead and drag and drop our dependent variable of interest into the dependent variables box. So immediately I get some results over here. We have our test statistic, which is 0.098, our degrees of freedom, and our p-value, which is 0.922, which is considered not statistically significant. For more information, we can go ahead and look at the mean difference between men and women, which is 0.073, as well as the effect size over here. So we can find our Cohen's d value and also get the confidence interval for that. And so with this information, we have everything that we need to interpret our frequentist result. Importantly, we can see here that this mean difference is our estimate, what we would expect the difference in hours to be based on this sample and this analysis in terms of hours. And we can see that this estimate overlaps with 0. So we don't have sufficient evidence to conclude that there is a difference here. And importantly, when we look at Cohen's d, is this the effect actually meaningful? Well, again, it's so small, so close to 0. And our confidence interval for the effect size overlaps with 0. So we don't have enough information to conclude that there's a statistically significant or practically significant difference here. So now we can move into the Bayesian analysis, and we'll select t-test, Bayesian independent samples t-test, and then we're going to go ahead and drag and drop the same variables as before into the corresponding boxes. Okay. Immediately we get out a Bayes factor, base 10 of 0.044 with an error of 0.5. So we can go ahead and make this a little bit more interpretable. When this value is less than 1, we have evidence in support of the null hypothesis. So the 1 here stands for alternative, 0 for null in this case. Alternative meaning that there is a difference between genders, null meaning that there is not a difference between genders. And so 1, 0 means that we're comparing the alternative hypothesis over the null. And so because this is less than 1, we know it's in support of the null. So we can flip the 0 and 1 to get a result that's much more interpretable. So here we can see that the data are about 22.571 times in favor of the null hypothesis relative to the alternative hypothesis. And we can go ahead and plot our prior and posterior for more information. You can see here, I did not specify a prior. I'm using the default prior available in Jamovi, which is very weak. As you can see here, it's very flat, loosely centered over 0. You can find more information down here. This is the default Cauchy prior, but essentially the Cauchy prior is centered at 0. That's the location and has a scale of 0.707. This represents our interquartile range. So in other words, 50% of the prior mass lies within the interval of negative 0.707 to positive 0.707. And so what this is doing, it's placing most of the mass of the prior over small to medium effect sizes, but the tails of the distribution still allow for large and very large effect sizes in either direction. So now we can see here with this dark line, this is our posterior. So once we've actually updated our prior information by the likelihood and data that we observed, we have really strong evidence in favor of our null hypothesis. We have everything that we need to go ahead and interpret the analysis. Now, for more information, perhaps you're wondering, well, what would have happened if I had used other priors or different types of priors? You can look at a Bayes factor robustness check, which is essentially looking at different priors, and in this case, it's widening the prior to see how it impacts the Bayes factor. So as we widen our prior, we actually see increasing evidence in support of the null hypothesis. But the results are relatively stable, right? They're all in the same direction. We're just moving from strong to very strong. So again, this supports our initial finding, or we're observing evidence in support of no difference between the amount of time that men and women spent online. So now we could return to our results. So if we're considering, do men and women differ in the time they spend online, again, not including email or work online, in the frequentist framework, we would report our results by saying the average difference in hours spent on the web between men and women is 0.07, with a 95% confidence interval from negative 1.53 to 1.38. Our Cohen's d is 0.004, which is meaningless. It's so small. And it has a 95% confidence interval from negative 0.07 to 0.08. So we can see here that both the average difference in hours as well as our effect size overlap with 0. So in the frequentist framework, this means that if we repeated the study over and over again, 95% of the confidence intervals would contain the true effect size. So recall, when we're working within the frequentist framework, probability is long-run frequency. So it's a long-run frequency of event over time. And so that's why we use this language over and over again over repeated sampling. And again, because in the frequentist framework, we are assuming that there's one single true value of the parameter of interest. In this case, there's one single true value for the average difference in hours spent on the web. And so therefore, this value can either be inside or outside of our 95% confidence interval. So that's why we are sort of using this dichotomous language. Now, considering the same question in the Bayesian framework, we would say that the median effect size of hours spent on the web between men and women is 0.004, with a 95% credible interval from negative 0.07 to 0.08. So again, we have the same effect size value as we observed in the frequentist framework, and our credible interval is overlapping with 0 here as well. And so we would interpret this to mean that there's a 95% probability that the true effect size is between negative 0.07 and 0.08. So notice when we are interpreting the interval here in the Bayesian framework, we can just interpret probability directly. And that's because probability in the Bayesian framework is the degree or relative plausibility of an event. And we don't assume that there is a single true parameter value, but instead we're assuming that there's many possible or potential parameter values. And so we're estimating that in the Bayesian framework. So we're able to make these direct probability statements, which are perhaps a bit clearer than the language we have to use in the frequentist framework. And again, the way that we interpret these results is really contingent on the underlying fundamental philosophical assumptions of these paradigms when it comes to parameters, data, and probability. So you may have noticed that the results are very similar, and they're in fact, the same when it comes to the effect size. And that's to be expected, right? And this is because the data set is relatively large. We have a couple thousand adults. And so what's happening here, since we're not using informative priors in the Bayesian framework, the likelihood is really dominating the analysis. Both the frequentist and Bayesian framework have the same likelihood function. And so that's really what's driving the results here. And so with a large sample, in this case, we can think we have really compelling evidence. It's going to overwhelm any prior assumptions that we have, and we get the same results. So now pivoting to the t-test example, do men and women differ in time they spend online? In the frequentist framework, we still have the results we reported before, but we would say we failed to reject the null hypothesis that the number of hours men and women spend on the web are the same. In the Bayesian framework, we could actually compute the Bayes factor. And so we can directly say that the data are 23 times in favor of the null hypothesis compared to the alternative hypothesis. So this difference is really important. In the frequentist framework, we're limited to saying that we fail to reject the null hypothesis, right? We either fail to reject the null or we reject the null, but we're never actually accepting the null or providing evidence in support of the null hypothesis. In the Bayesian framework, by using Bayes factors, we can say that the data suggests that the null hypothesis is about 23 times more likely than the alternative hypothesis. So we can directly support or provide evidence in support of our null hypothesis. And this is really powerful because this is something that, again, we can't really do in the frequentist framework. So we can accumulate and directly support our null, which is really relevant in the context of scientific research where null findings are and can be oftentimes very meaningful. So with that, this is one benefit of using Bayesian analysis is the ability to support the null hypothesis. Thank you so much for watching, and I'll see you next time.